Hi, I'm going to do a video on recursion. I just got a Wacom tablet and I'm excited to use it, and I've been practicing writing with it, so we're going to see how this goes. I'm sort of shamelessly ripping off the style of Khan Academy, so this is going to be sort of your best value brand Khan Academy video on recursion. Yeah, it's like Western family style, like the mac and cheese, and you make it, but it's got like half the powder, and you're like, well, hell, it was 50 cents. Anyways, that's going to be your less cheesy version of recursion. So, anyways, last time I was talking about how recursion is a concept in computer science that matches just plain old math really well. So let's look at the Fibonacci sequence for an example. This is a famous series. Now everything's gonna be slower because I'm on this, but it's cooler, so let's just go with it. It's a famous series of numbers. It was sort of defined by the famous mathematician Leonardo Fibonacci. He was a banker, I think, a merchant, actually, and he was really into math, and his travels informed him on mathematics, and he brought back the idea of zero to Europe from the Near East. Anyways, this is the sequence, the series that he's most notably recognized for. So this is just the first few. So we can think, okay, what we're going to do is you take a value. So it's we have, let's say, the 0th number, the first number, second number, third number, fourth, fifth, sixth, seventh, eighth, ninth, and 10th. So you compute each number by adding the previous two. So I'll take, let's say I have a number, or let's define this. So I could do like Fibonacci of 4. Well, that's going to be Fibonacci of 3 plus Fibonacci of 2. So the third number in the sequence is 2, and the second one is 1. So that's how we get 3. More generally, we have Fibonacci of n is going to be Fibonacci of n minus 1 plus Fibonacci of n minus 2. But there's a couple other details here. You need base cases. So Fibonacci of 0 is going to be 0, and Fibonacci of 1 will be 1. Because this above equation, fib of n, we need it to terminate. So these are, that's not going to work. Oh, that is the wrong thing. So right here, I'm going to put just b for base case, and this is our recursive case. So if you remember last time, recursion always follows this pattern of there's at least two cases, a base case, at least one base case, and a recursive case. So the base case is some particular value, in this case 0 and 1, we have two of them, and then the recursive case is, well, we take the last two values and we add them together. So we produce this sequence. Now if we change out these base numbers here, the base case values, we'd actually generate a different sequence. So that's actually what Fibonacci was thinking about. 0 and 1 is just coincidentally what's most common in the popular mind, but he was looking at all sorts of different, well, what if you have different base cases, you get different sequences, and that's kind of interesting. So anyhow, this is sort of famous mathematical equation. Now let's translate it to code. So now I'm going to attempt to transition smoothly. Oh, look at that, into IntelliJ. Now you hear the click clack of my keyboard. I'm using all my favorite input devices. Now I've defined, now let me write the Fibonacci function here in Java. So again, because it has that recursive property of, oh, the current value is the two previous added together, we can really easily code this. So let me just give this a run right now. See what happens. It took a second longer than I wanted. So we were computing the first 4 numbers in the sequence. Fantastic. It's not really doing anything. I just have it stubbed out. Again, that's just sort of a pro tip, a pro sort of debugging tip. What I'm going to do here is define those cases. So I'll do the base case and base case 0, base case 1, and let's do recursive case. So this will be a nice use of recursion. So if, again, the way I'm setting it up, I mean, if you look at different examples, you might see people define the series a little bit, because I'm doing a 0th number. Probably pure mathematicians don't like that as much. But hey, it's computer science. We typically use 0 as our first thing to count with, our first integer to count with. So here on line 6, I did not mean to do that. We're going to define, if we're asked for the 0th number, we just return 0. Down here on line 11, if we're asked for the first number, we're going to just return 1. Again, those are just the defined base cases. Now we're going to do the recursive case. So this is the fun part. So I can do index minus 1, fib of index minus 2. Fantastic. So now let's give it a run and see what happens. Hey, that's looking promising. Let me expand the range a little bit. Let me bump this up to, I hesitate, but we'll see. We'll give it a whirl and see what happens. Now there'll be, oh yeah, I did less than equal to. Let me get it right. Okay. Ta-da. Now look at this. We produced it just like I said. So this is why recursion's so nice when coding. Look at this. I produced this series. I mean, apart from me printing it out, I didn't use a loop at all. I just defined the function in terms of itself. So now let's dig a little deeper into it. I'm going to print out a couple values. Let's use printf again. I'm going to say calling fib of. So we'll see what happens here. Actually, that was unintentionally awesome, I think. No, well, no, it's just a screen. This is just a wrap. I was hoping I got some weird sort of triangle property by accident. Never mind. Disregard that. Let's run it again. Okay, now we have all these calls. You see this? So every time this function is called, it prints calling. And now you can see as I scroll through here, there are a lot of calls. Now, why is that? Notice for each time this Fibonacci function is called, it's going to turn around down here and make 2 more calls in the recursive case. Is that a problem? Well, let's go see. Let me click back over to this. So now let's go down a little bit, or up a bit rather. So What is that all about? Well, if each call produces 2 calls, let me just do Fibonacci of 4. See if I can fit this all in here. So when I call Fibonacci of 4, it's going to call fib of 3, and it's also going to call fib of 2. Oop. Yeah, look at that. Little arrows, little arrow. Well, okay, maybe not the arrows, but anyways. Now, when it calls Fibonacci of 3, we're going to get Fibonacci of 2 as one call of this, and Fibonacci of 1, because it goes for 2 previous values. And this is going to produce Fibonacci of 1, and this will do fib of 0. Oh, and I need to break this one down further. I'm going to get Fibonacci. Oh, don't want that. Here comes the eraser. Yeah, I did it. Okay. And fib of 0. Oh, look at that. So if we can see at each level here, this is going to spawn, 2 times 2 more calls. So we're going to have 1 on this level, 2, 4. Now if this level only had 2 in it, but if the pattern continues, we have 8, 16. Oh, that's not very good. 16. Okay, 32. Effectively, whatever it's going to be, approximately 2 to the n, where n is the number being called the index of the number we want. So where it's this n here. That's sort of a problem. This, however, it's not a problem with recursion in general. It's just a bit of a warning and a preview of, well, we can't just do things naively and expect the computer to work well. Because if we can't just throw, oh, now give me the 1000th Fibonacci number. If this is growing to the nth power, if it's 2 to the n, if we ask for the 1000th thing, that's going to be a big problem. Right? Think of all that work that's being done. And we can see here there's a bunch of work being repeated. So we see like fib of 1 is in here multiple times. Fib of 2 is in 0 is in here multiple times. 2 is in here multiple times. That's sort of a different topic for like how are we going to avoid all this wasted effort. But I just want to trace for you what is actually happening. So that's basically recursion in a nutshell, with Fibonacci as an example, and just a little bit of the perils of, well, you got to be careful. You have to be careful in general when you code, but especially if you're recursively, if you're setting up a recursive function, you don't accidentally generate 2 to the n function calls, which is a big problem. But yeah, so that's a little bit of an introduction to time complexity is the term for that, which I'll cover in depth or a little more depth later. So yeah, that's it. Thanks for watching.